When we look at the sky, everything seems stable. The moon rises every night, the oceans move in and out with the tides, and days always seem to last 24 hours. From our daily point of view, nothing appears to change. But in reality, a very slow and powerful process has been happening for billions of years. The moon is slowly moving away from the Earth, and this quiet movement is gently changing how our planet behaves. It affects the length of our days, the strength of our tides, and even what Earth's future will look like. This change is so slow that no human will ever feel it directly. Yet over millions of years, the effects become very large. To understand what is happening, we need to look at how the moon and Earth interact through gravity, tides, and motion. This story is not about sudden disasters or dramatic events. It is about patience, time, and the steady laws of physics working without pause. Earth and moon are not separate objects moving independently through space. They form a connected system. The moon's gravity pulls on Earth, and Earth's gravity pulls on the moon. This mutual pull shapes the oceans, affects Earth's rotation, and controls the moon's orbit. The moon is responsible for most of Earth's ocean tides. When the moon's gravity pulls on the oceans, it creates bulges of water. One bulge forms on the side of Earth facing the moon, where the pull is strongest. Another bulge forms on the opposite side, caused by the balance of forces in the Earth-Moon system. As Earth rotates, different coastlines move through these bulges, creating the regular rise and fall of sea levels we call tides. But tides do more than move water. They also move energy. And over very long periods of time, that energy transfer changes both Earth and the moon. Today, one full rotation of Earth takes 24 hours. This feels normal to us, but it was not always this way. Long ago, Earth spun much faster on its axis. That means days were shorter. Hundreds of millions of years ago, a single day was about 23.5 hours long. Go back even further, and days may have lasted only 10 hours or even less. Scientists did not guess this randomly. They found real evidence preserved in ancient rocks and fossils. Some ancient sea animals, especially shell-forming creatures similar to clams, grew in daily layers. Each day, the shell added a thin line, just like a tree adds one ring each year. By counting these tiny daily layers in fossil shells, scientists can tell how many days existed in 1 year long ago. In one important study, researchers examined fossils from the time of the dinosaurs and found about 372 daily layers in a year. That tells us Earth rotated more times per year, which means each day was shorter. When the moon first formed around 4.5 billion years ago, it was far closer to Earth than it is today. Most scientists believe the moon formed after a Mars-sized object crashed into the early Earth. The impact threw huge amounts of molten rock into space, which later gathered together to form the moon. At that time, the moon would have looked enormous in the sky. It would have risen much larger than it does now and created incredibly strong tides. These tides may have reached far inland, reshaping coastlines and affecting early life on Earth. Because the moon was closer, its gravitational pull was stronger. This strong pull played a major role in slowing Earth's rotation and starting the long process that continues today. The moon is moving away from Earth because of tides and friction. Earth rotates faster than the moon orbits it. As Earth spins, the tidal bulges created by the moon's gravity are carried slightly ahead of the moon's position. These bulges are not perfectly lined up. This misalignment matters. The bulges act like handles that Earth's gravity uses to pull on the moon. The forward-shifted bulges tug the moon ahead in its orbit. When the moon is pulled forward, it gains energy. That extra energy moves the moon into a slightly higher orbit, farther away from Earth. At the same time, Earth loses a tiny bit of its rotational energy. That loss causes Earth's rotation to slow down. When rotation slows, days become longer. So this process does two things at once. It pushes the moon away and stretches the length of Earth's day. The oceans are the key players in this process. As tides move across the planet, water rubs against the seafloor and coastlines. This rubbing creates friction. Friction turns motion into heat and slowly removes energy from Earth's rotation. Shallow seas and continental shelves are especially important. They increase friction and make energy loss more efficient. Over millions of years, this tiny loss adds up. Think of Earth like a spinning top. Friction from the oceans is like a gentle hand touching the top again and again. The top does not stop suddenly, but it slows down little by little. The moon moves away from Earth by about 3.8 centimeters per year. That is roughly the speed at which fingernails grow. This number is not a guess. It comes from extremely precise measurements. During the Apollo missions, astronauts placed special mirrors called retroreflectors on the moon's surface. Scientists on Earth fire laser beams at these mirrors. The light travels to the moon, bounces off the mirror, and returns to Earth. By measuring how long the laser takes to return, scientists can calculate the exact distance to the moon. Because the speed of light is constant, even tiny changes in distance can be detected. Decades of laser measurements show that the moon really is drifting away year after year. As the moon moves away, Earth's rotation slows. This makes our days longer. Right now, the change is extremely small. A day becomes longer by only a few milliseconds per century. No human can notice this directly. However, atomic clocks are so accurate that scientists must occasionally add a leap second to keep our time systems in sync with Earth's rotation. Without these adjustments, clocks would slowly drift away from the natural day-night cycle. So while the change is tiny, it is real and measurable. As the moon moves farther away, its gravitational pull weakens. That means tides will slowly become less powerful. The difference between high tide and low tide will shrink over long periods of time. This does not mean tides will disappear soon. Coastlines, ocean depth, weather, and storms will still create strong local tides, but the global trend is toward calmer tides. Many marine ecosystems depend on tidal movement. Tides bring nutrients, mix water, and shape habitats. A future Earth with weaker tides would be very different for coastal life. In theory, Earth and the moon could one day reach a state called tidal locking. The moon is already tidally locked to Earth, which is why we always see the same face of the moon. If Earth became tidally locked to the moon, one side of Earth would always face the moon. A full Earth rotation would take about 27 current days. In that situation, tides would barely move. Instead of rising and falling daily, water would form almost permanent bulges. But this future is extremely unlikely to fully happen. Long before tidal locking could occur, other cosmic events will intervene. Sun is not constant. Over time, it is slowly becoming brighter. In about 1 billion years, increased solar heat will cause Earth's oceans to evaporate faster. With less water, tides will weaken dramatically. Without strong tides, the process pushing the moon away will slow down or stop. Billions of years later, the sun will expand into a red giant. At that stage, Earth and the moon may be destroyed or transformed beyond recognition. So the Earth-Moon story will end not because tides finish their work, but because the sun changes the rules entirely. One noticeable effect of the moon's retreat involves eclipses. Total solar eclipses happen because the moon appears almost exactly the same size as the sun in our sky. As the moon moves farther away, it looks slightly smaller. Over tens of millions of years, total solar eclipses will become rarer. Eventually, the moon will no longer fully cover the sun. Future eclipses will mostly be annular, with a bright ring of sunlight visible around the moon. This reminds us that even beautiful, familiar events are temporary on cosmic timescales. Scientists can read Earth's past by studying tidal patterns preserved in rocks. Some sediment layers show repeating rhythms linked to tides, seasons, and Earth's rotation. These records help scientists reconstruct ancient climates and day lengths. Shorter days affect winds and weather. Stronger tides affect coastlines and ocean chemistry. All these factors influence where life can survive and how ecosystems develop. The slow movement of the moon helps scientists test climate models and understand Earth's long-term stability. When astronomers study distant planets, they look at how moons interact with their planets. Large moons can stabilize a planet's tilt, help control climate, and create tides that support life. The Earth-Moon system is a nearby example that helps scientists imagine what might be happening on distant worlds. Understanding our own planet helps us understand the universe. When you watch waves rise on a beach or see a total eclipse darken the sky, you are witnessing a moment in a very long story. The moon is slowly moving away. Our days are quietly growing longer. Coastlines are changing at a pace too slow to notice, but not too slow to matter. Earth is not frozen in time. It is mid-chapter in a story written by gravity, motion, and time itself. The changes are gentle, patient, and unstoppable. And they remind us that even the most familiar parts of our world are always quietly becoming something new.